Hi, let's talk a little bit about number systems. There are a variety of different number systems that we can work with. Of course, the one that we're most comfortable with is decimal, base 10, but there are many other number systems, and we're going to look at three of them today: binary, octal, and hexadecimal. But before we understand those number systems, let's just briefly talk about what it means to be a positional number system. Basically, all modern number systems are positional, and this means that the weight of a number depends upon its location in the number. A good counterexample of this, for example, would be Roman numerals, which are not positional. In those cases, it was different actual letters that were used to represent the position rather than its location, to represent its value rather than its position in the number. But let's turn our attention to modern number systems. Here you can see that I have, for example, the number 123.45. And so in this case, you can see that the 1 is in the place of 100s, 2 is in the place of 10s, 3 is in the place of 1s, 4 is in the place of 1/10ths, and 5 is in the place of 1/100ths. It's something that you're very familiar with, very comfortable with, but you may not think about it all the time to realize that when we're writing this number, we're actually saying that this is 100 plus 20 plus 3 plus 0.4 plus 0.05. It's just the way that the number system works, is that the location, the position of the number determines its weight. Now, decimal numbers are those that have 10 different possible digits that could go in each of those locations. So you can see here that we have 10 different possible combinations, or 10 different digits, 0 through 9. And this is something that we're going to have to become accustomed to, is that the first value is always going to be 0. So if we're talking about base 10 or decimal, we only go up to the value of 9. There is no one digit that can be used to represent the number 10. If we want to go to 10, we're going to have to include a second digit as well. So if you think about this, we can represent a number, a decimal number, positionally, but of course it doesn't have to be a decimal number. In addition to decimal, we can also consider binary. And so binary numbers are the next thing that we're going to consider. So if decimal numbers are the most natural numbers for humans to use, why is it that all digital devices and computers use binary numbers instead? And what is a binary number? Well, a binary number is simply a number that uses a base 2. Just like in decimal, the weight of each digit will depend upon its location in the number. So you can see here that, for example, this digit is going to correspond to 2 to the second power, which is 4. This digit will correspond to 2 to the first power, which is 2, 2 to the 0th power, which is 1, 2 to the negative 1 power, which is 1/2, 2 to the negative 2 power, which is 1/4. And we can represent any number using combinations of binary bits, just as we can represent any number in decimal. I guess I should clarify, there are some numbers that can't be represented precisely or perfectly, like, for example, the number 1/3 cannot be represented exactly in decimal, but most numbers can be represented with sufficient level of precision. So you can see here that we're breaking this number down: 4 plus 1 plus 0.5 plus 0.25, just as we broke the previous number down. Now, each one of those individual binary numbers, each one of those binary digits is called a bit. And if you have 8 of those bits, then that's going to form what we call a byte, B-Y-T-E. And if you have larger groups, 16, 32, or 64, that'll be referred to as a binary word. So we have bits, we have bytes, we have words. There are other combinations as well, but those are the three most, sort of the most important ones. So now that we understand how binary numbers work, why is it that we use binary numbers? And the short answer, I'll let you read the full text, is that binary is very, very easy. And things that are very, very easy can be done very, very fast and with very, very high level of reliability. And so what we really need from our computer is to work quickly and to work reliably, and binary is definitely the best way to do that. I've done some research with ternary, which is base 3. The problem there is that in addition to being on and off, you also have to have a setting that's halfway on and off. It's like a dimmer switch, and it gets very confusing. And so confusing yields results that are not as quick or reliable as we'd like them to be. So if we have decimal and we have binary, there must be a way to convert between those two bases. And yes, there is, as a matter of fact. And the thing that we're going to end up this particular video with is talking about the powers of 2, because the powers of 2 are going to be very important to us as we're doing these conversions. I've written out here in figure 3 the first 10 powers of 2. And I really think that it is absolutely worth your time and effort to memorize these 10 powers of 2. Let me just take a minute and point out a few things here. 2 to the first is 2. You you know that off the top of your head. I'd like to think 2 squared, 2 times 2 is 4, 2 times 2 is 2 times 2 times 2 is 8. Those 3, I'm guessing that you can do right now without having to give any extra thought to. 2 to the 4th, well, that's 2 squared times 2 squared, which is 4 times 4. Sometimes I'll remember it as 2 to the 4th is equal to 4 to the 2nd. 4 to the 2nd is 4 times 4, which is 16. Now, 2 to the 5th is a little harder, but what I do there is I just remember that it's double 2 to the 4th. So if you double 16, then you're going to get 32. 2 to the 6th is easy because there's a 6 there and there's a 6 in the result. So if you have a general memory that 64 is a power of 2, then 2 to the 6th is definitely going to be the one 6 gives 6. So 2 to the 6th gives 64. 2 to the 7th, again, I don't remember that one itself. I remember that it is double of 2 to the 6th. 2 to the 8th is 256. I've got to tell you that 256, I wrote that it is a VIN, not a vehicle identification number, a very important number. If you don't already recognize 256 as being a very, very important number, you will before this class is over. 256, if we all had 8 fingers, or if we had 16 fingers, 256 would be a very round number. It is 2 to the 8th power, which is 2 to the 2 to the 2 to the 2. And so that is about as round as a number can get. So I'm not saying that maybe off the top of your head, you know, 2 to the 8th is 256 right now, but I am saying that eventually it's going to become very second nature to you. 2 to the 9th, well, that's 256 times 2. And then 2 to the 10th is 1024, another number that you're going to become more comfortable with. And once you know that 1024 is a power of 2, then you have 10 and 10. And so 10 gives 10 just as 6 gave 6 up here. Okay, so if you know those 10 numbers, then you can combine them together and you can say, for example, what is 2 to the 18th power? Well, 2 to the 18th is 2 to the 8th times 2 to the 10th. 2 to the 8th, well, that's 256. I have that memorized. 2 to the 10th, that's 1024. I have that memorized. And 1024, we're often going to approximate that as 1,000. So we're going to say that this is often written as 256 times 1,000 or 256K. 2 to the 20th is 2 to the 10th times 2 to the 10th. 1,000 times 1,000 gives a million, or we'll refer to it as 1 mega. So if you have a megabyte, for example, that's 2 to the 20th. 2 to the 30th is 2 to the 10th times 2 to the 10th times 2 to the 10th, which is a billion, or 1 giga. And 2 to the 40th, well, that would be 1 trillion, or 1 tera. So that often is used to help you to convert larger numbers. So at this point, I'm going to go ahead and halt this video so you can do the self-check. You should now be ready to solve the powers of 2 example problem.